Hi, do you remember that I told you that this serial port was difficult to make because we needed state machines? So here I have a simulation of a serial port pushing out data. So you can look at that. It will be a short video. So this week I've been learning state machines, and this is from a video on the Open EDX part of the study, so everybody can log in there if they want. Just let me know if you want the details so you can learn. Anyway, we have a state machine. It basically looks like this, and what a state machine does is that it resides in one state, and then if the inputs change, the next state can then be clocked into a register, which again feeds back to the next stage. So what that means is that if you sit here, and in this example it's a intersection with a green and red light, and if there is a car coming, then it changes state, and then a timer starts, and if it hasn't timed out, it will stay in that state, and if it times out, it goes back. And here you can also see the color is changing. But this is an ambiguous way, slightly ambiguous. So therefore we use, instead of finite state machine charts, we use ASM, which is algorithmic state machine charts. Because then you know exactly how many clock cycles it takes for each of these parts of the drawing and what kind of hardware you get. So I've done that. Quickly show you how to set up the state machine. So here you can see the SEQ process, which takes a reset and a clock. It doesn't do very much, does it? So when it gets a reset at the startup, then the present state is at the start. That's important. So you always have some entry point in your... let's see... yeah, if you look at this, this is the timer I'm using. So, yep, this is the one I'm using, and you can see we have a reset at the top here, and then we want to send data out on the serial port. So we want to know if there's data at all. If it isn't, it will just reside in this empty box, which is the start box. And if there is a shift data register loaded, then we will continue and get into the initialization state, which is what this means. If it says loads reg, it means this signal is high. It's an assumption, so you don't have to say equals 1 actually. And the counter is set to 7, so if there's an arrow, that means it will be remembered. But loads reg, when that's high in this state, it will be low in this state. And also there's a clock cycle between this one and this one. Okay, so this is just an empty state, and the reason for that is because I needed something. I needed a clock cycle when I go back up here again. We'll look at that. So we look if the timer has timed out, and if not, then yeah, so you also have to set the timer. I haven't written that here, but it should say start timer. So, but that was something I worked on tonight. It was difficult for me to understand. So what I did was I just listened to the load S register. So if the S register is loaded, then I start the timer. Anyway, too much detail. So if it's not timed out, it will check if the counter is going high. So why does it do that? And you can see that it just resides in this loop if it doesn't, if count isn't going high. The reason for that is because this timer or this serial port is not pumping out data at the speed of the clock. It's pumping out data at the speed of count. So therefore you have to wait for the count, which it has the speed of the baud rate set by the timer. So if there comes a count, then we shift out one bit, and we also send out a signal to the counter to decrement. So, and the reason why I don't have a counter inside this, if you were doing programming, you would just say counter minus minus to decrement the counter, but you can't, because this is a there was something I learned today. This is a what is it called? Combinational logic. There's no, if you look here, you can see you have a rising edge phi 2, and that means that this one is sequential, and it and this assignment next state to present state is done only at the rising edge. Therefore this is a register assignment. But down here this is actually just logic, so you can't have sequential statements, and then you can have statements, but you can't make sequential logic out of combinatorial logic. So that I didn't understand that, but so the only thing I do, and you can also see that from here, the only sequential thing you have in this state machine is that state itself. The output is just a function of the state, and actually you can see that here. If we are in one of these states, you can see the outputs are, like for example load sreg is an output, it's 1, and why don't I say it, okay, and then I say it's 0 here, but it's 0 anyway because it has default values. So in theory I can remove that part. Yeah, and you have some outputs there also. They are directly dependent on the state. So there you have that. So yeah, so not to make this video long, let's try not to shake the camera so much. So what are we looking at here? In the datasheet they say that if the processor sends a byte to the shift register SDR, then if the count is running from the timer, it will start immediately and send out data on the count process. So here you have count, right? But I'm converting it into a pulse with a length of 1 clock cycle, because it's easier that way. So, and they also say something else. When it's finished, it stops sending data. That's all. That's natural. So you can see that it sends 8 pulses, and then the data comes out. So let's see, does it actually work? Well, if you look at this shift register, which I called DFF, you can see that okay, we write the value 1 into C, which is actually the serial data register, and that works. And then after some time it starts shifting it out, So you can see that bit will move through the register. These are the bits in the register. And it stops. So, and why does it start again? Because I do another write up here. But there's another thing, another feature, is that you can have continuous data stream. If you manage to get the processor to write before the data transmission ends. So here I write another, what should I say? I write another data into the SDR. You can't see it change because it's the same data. That was a bit silly. But anyway, yeah. So when you have 8 pulses, 1, 2, 3, 4, 5, 6, 7, 8, you can see the SDR loaded is a signal which I spent like an hour to get working. It remembers that there is new data, and when the data is starts shipping out, it resets, such that if you get another pulse, it will go up again, and remember that it should continue. So you can also see this pulse in the beginning here. It's very short because data is written to the register and then it's pumped out straight away. Therefore the data register loaded bit is very short. But here it's longer because the data is waiting for its turn to be shifted out, because this bits has to be shifted out first and then it starts shifting. So you can also see the state machine. Let's zoom in here. Sorry for the shaking, this is because I'm using one hand now. So let's see. There, that's better. Okay, you can see it starts in start. So you have start on the top there. And then it checks for SDR loaded. So if SDR loaded is high, then it goes into init. So SDR loaded is a signal which is generated by write flag, and then it's reset by the load sreg. So, and that was what I explained just a minute ago, to remember that it has been, there is new data and the data has been loaded. So there's a difference there. So there it comes, and then the state is changing. Let's zoom a little bit more, see what it says. Okay, so it goes into init. And then the init is just one clock cycle, you can see, because it goes into wait. So this one this waits for a count pulse. So we have a wait count. So let's see if you can get some counting here. Let's see, where is the count? There we have a count. There comes a count, and then I have converted that to a count flag. And straight after this, here you can see the next state, which is, next state is dependent on the inputs, therefore it changes when you get the count flag. But however, the current state won't change before the clock. So therefore you can see here, the next state changes because of the count flag, and then you get a positive edge, and then we go from shift to shift, or from wait count to shift, and then back again to wait for next pulse. So yeah, and you can also see that these the bit is moving here, so from this part to this part. So yeah, that's what I wanted to tell you. Time is running here, so been studying this week, and I have a lab assignment, and it's difficult stuff. Actually, this was perfect for this serial port module that I'm working on for the CIA IC for the Commodore 64. Yeah, so thank you for watching, and you can see we're getting somewhere here. Interrupt, IO port, serial port, and test benches. So yeah, so there's more to be done, but here we go, and hope to be finished soon. So thank you for watching. Bye bye.